Изображение переведено.
Ну, зеркально. Это же лайк. Главное, чтобы он был. И кнопка donate по поводу.
Там все еще транслируют?
Я надеюсь.
А я тоже надеюсь.
Бессмертно мне напишут.
Ну да.
That's not cool. All right. The first semicolon is in 1490 by King August. Like Herman Melville. For example, today, for lunch, I ordered a cheeseburger. Too short. Semicolons are also used to avoid confusion in cereal. Try to for practice, catch 2 old nut cereals, across 4 semicolons. 10 pieces of bacon, ham, or sausage, and cottage balls, pancakes, or grapes. Well, it's a breakfast of chicken. That would be probably semicolons are used for one minute. Quick cookies. You can go through your whole life practicing semicolon. Why? What do you think about semicolons? Leave your thoughts in the comments below.
Well, hello, single people. Does your phone screen have a permanent smudge from swiping left? Dating on the apps can feel like a constant game of tag, and if you're a cigarette, you're not welcome. According to new research, 1/3 of people who use online dating have never gone on a date with someone they met as a result. It seems like meeting someone you met should be easier than ever, but the struggle.
And set. Whoops. Probably should have picked on that.
Dave made a few typos in his message, but he hopes his potential dates won't mind.
Remember much?
Reality check. Potential therapist judge your grammar. Just 2 spelling errors in a man's online dating profile can reduce his chances of getting a match by a whopping 14%. Holly thinks all those extra punctuation marks make her sound really fun. Dave thinks Holly sounds a little over the top. Punctuation seems a bit desperate. Dude, calm down. She's probably really nice. Whoa! Looks like Dave is writing more in the piece there. He figures writing a lot will make him seem interesting. Holly isn't convinced. She's seen this before, and she knows long responses don't necessarily mean a person is deep. The last guy she met who would know what was on my dating profile probably should have written nicer things. Hey, fun fact, guys use 22% more words in their online dating profiles. You go with the details always, but keep in mind that any has had more luck with the ladies. But smart grammar gives you some advantages.
To whom am I attracted? You.
We have a winner. Guys who properly use whom in their online dating profiles have scored 31% more matches with the women they messaged.
But what about me?
Well, you're going to get 17 times as many matches as your friend there. There's a lot of fish in the sea. It's just about getting the right one each time. It's important.
Заплатишь Филиппу?
Check the links below for more writing guidance.
Ладно, я так понимаю, за 4 минуты до начала можно начать всех развлекать. Is there anyone who doesn't speak Russian in the room right now? Okay. Интересный факт, последний раз Kievfprog был игровой 4 года назад. Вот. После того, аудитория повысилась, мы здесь перестали поститься. Теперь получилось так, что в августе всегда период отпусков, мы уже 3-й раз делаем митап с анонсом за 2-3 дня. Один раз мы делали метап, когда приезжал Михель Тринке, он был, по-моему, из Бельгии и рассказал про кожу. Один раз у нас был метап про... Приезжал Иван Перец, который занимается, собственно, он является PhD-студентом, отца функционального реактивного программирования, он приезжал к нам, когда мы хочется все. И сегодня я вот слежу за воскресенье в Твиттере, и пишут мне Собственно, Джастин говорит, типа, я тут в Киеве, а я как бы слежу за работой этого парня уже как бы полгода, и я был очень ужасно отстроился, и мы внезапно опять организовали. Вот. Если кто смотрит нас на Ютубе, то всем привет. Это очень прикольная тема, потому что когда мы начали пользоваться ивентбрайтом, люди наконец-то стали иметь возможность отказываться от того, что они придут, ну или как бы отдавать свой билет назад, и мы наконец-то можем точно оценивать, сколько людей придет. Вот. Прямо для таких же мы сделали канал на YouTube. Сейчас мы еще подождем минут 5, и можно будет начинать. Кстати, на этом Kievfprog я сделал анонс в группе искусственного интеллекта. Думаю, есть ли тут уже знали люди, которые... Окей, все. Будет такая смесь тусовок. Это ходить. Также ждите, подписывайтесь на наш канал на YouTube. Мы стримим там раз в год. Поэтому каждый год вы будете находить интересный контент. У нас 2 зрителя. Похоже, я и мой телефон. Также ждите, подписывайтесь на наш канал на YouTube. Отлично. Были какие-то трудности найти офис?
Да, все. Консультация, куда ты находишься.
У меня была проблема при неинтересировании. Я думал, раз они открываются, то надо знакомые лица.
And the papers want to know whose shirts you wear. Now it's time to
Я захотел. Мы сегодня стримим лайв на YouTube. Это наш второй стрим.
Я что не догадался.
Что интересно, что канал Kievfprog создал Руслан Шевченко. И у него стоит автоматическое уведомление в Киеве, когда что-то происходит в этом канале. Как-то я полгода назад решил почистить видео, у него было на Twitter 10, потому что он перезалил какое-то видео, а сейчас он стримит лайв на канале Kievfprog. На камере вот. Justin great. Sorry, we hit some traffic. GPS says about 7:15, so возможно 10 минут, 10-15 минут мы еще будем развлекаться сами с собой.
There's something wrong. Can you hear me, Major Tom? Can you hear me, Major Tom? Can you hear me, Major Tom?
Что, пока хорошая тема на сайте разминации, я знаю, недавно прошел прикольный хакатон с участием этих методов. Собственно, давайте сделаем перепись. Смотри, кто есть хаскилисты. Или кто хотел пытаться следить за комьюнити хаскиля. Окей, 2 человека. Еще 2 человека ржут, потому что они как бы были на ивенте, на который хочу сейчас позвать их пригласить. Короче, произошел хаскиль в Цюрихе. Нет, не хаскиль, Цюрихак. Да, точно, другая конференция. Вот, и это, походу, там 3-й год подряд, так понимаю. Андрей, ты был?
Я был.
Расскажи что-нибудь, как там, ты видел этот метод сзади, спереди, сбоку, правильно?
Я его вижу 2-й год.
Ты видел автограф, ты взял у него автограф или...
Нет, я оставил его автограф.
И что вы делали там на хакатоне?
Ну, в Швейцарии хорошие горы, хорошие речки, хорошие озера. Ну, где-то вот этим я на хакатоне и занимался. Вот, Эдвард Квет рассказывал всем про C++, аудитория благочестиво внимала, вот, глядя на мешанину из темплейтов, макросов и прочих достижений C++ строения. Вот, и радовалась, что в Haskell этого всего нет.
Ты что, на чем там работали? В Кабал фиксили или какой-то у вас отдельный проект был? Или наконец-то попрограммировали на баше там?
Чемпионат по программированию на баше был в другом хакатоне.
В офисе?
Выше PowerShell.
Окей. Ну да.
Ну, как-то вот этот хакатон был слабенький, потому что такой курортный городок на озере, и поэтому такой выходишь, смотришь на озеро, подцепишь, потом делаешь вид, что ты что-то пишешь. В прошлом году был в офисе Гугла в Цюрихе, вот там было так хардкорно, всех в одну комнату загнали, дверь закрыли, сказали по этажу не шастать. Вот, и все так бодренько, 3 суток. Джобы были. Ну так, по ID-карточке. Вот. Там была работа, а в этот раз как-то не особо.
А что, собственно, делал Кмет? Я вот так понял, короче, Кмета была презентация про то, что он на C++ делал какие-то штуки для Sims, да? У него была идея, что он берет какие-то C++ коды, а там автоматически векторизуется. А вопрос какой-то сзади ответ.
Я хотел сказать, что там есть сейчас синдром проблемы, там есть оптимизация на граниках, polyhedral models. Там, к сожалению, проблема в том, что синус оптимизации и векторизации никто не рассматривает в рамках дискретной оптимизации на многогранниках. То есть сейчас вот есть, ну, есть в Haskell есть backend LLVM, и он, по идее, как бы должен был бы там что-то векторизировать, но в LLVM векторизация сломана, поэтому polyhedral info. Да, оно самое. Да. Короче, это оптимизация на многогранниках дискретная, которая позволяет автоматически векторизировать код. В основном рассматриваются задачи, полные задачи типа взвешенного рюкзака, там boundaries рюкзака при распределении памяти, раскраски графов на этих многогранниках, то есть там есть ресурсы памяти, там есть какие-то алгоритмы cache oblivious, которые распределяют использование памяти, то есть у нас есть какая-то иерархия памяти, распределяется точечками на этих многогранниках. И, в общем-то, сейчас проблема в том, что автоматическая векторизация, она не до конца использует вот эти вот модели на многогранниках. То есть мы бы могли спокойно взять, сводить NP-полные задачи, которые сейчас решаются генетическими алгоритмами, алгоритмами, всякими муравьиными задачами дискретной оптимизации.
Так,
как вот этих вот моделей.
Я правильно понял, что идея использовать вот эти штуки для оптимизации внутри C++ компилятора, или это само либо
это в LLVM давно юзается, и LLVM сейчас у него сообщество разрозненное, получается, что вокруг LLVM есть вот эти обвертки, и как бы они работают, но, к сожалению, они пока в мейнстрим LLVM не были интегрированы полностью. То есть это на уровне научных исследований и практически оно сейчас нигде не используется, хотя выхлоп, ну, очень хороший. То есть если бы они это все завязали, было бы всем очень хорошо, текстилистам в том числе.
Я, кстати, где-то видел идею использовать вот этот инфо, оттуда в каком-то хаскельном чем-то.
Ну, там очень хорошо, красиво все лекторизуется. Просто я в последнее время занимался исследованием компиляторов языков. Последнее это где-то, ну, лет 8, где-то так. Кручусь, слежу, смотрю, что люди делают. Сейчас, даже если сравнить по выхлопу с LLM, то есть там еще есть куда двигаться, LLM не идеален. Там задачи интеллигентного вычисления, задачи автоматической векторизации, параллелизации, они как раз таки могут быть решены вот этими методами. Потому что у нас мы можем внедрить там метрики, весы, там, допустим, стоимость работы с памятью, там, стоимость различных динамопингов. То есть это все может быть описано в рамках вот этих вот моделей на грани. И потом, ну, решая задачу дискретной оптимизации, можем не страдать там индийскими алгоритмами и прочими вещами, которые могут выполняться месяцами, долго не выполняться. То есть там сейчас в рамках компилятора очень много проблем не решенных.
Это TSD такой или индустриальные задачи, которые
индустриальные задачи.
18 исследования компиляторов?
Ну, индустриальные задачи. Ну, IBM там тоже делал много чего делать, много чего писать, у них ничего не получилось. Да, я там крутился немного.
Раз у нас такой машин-лернинговый метод, ты знаешь что-нибудь про людей, которые пытались нейросетки использовать для того, чтобы оптимизацию генерировать?
Да, я знаю очень много случаев, когда люди пытались обучать нейронки индийским алгоритмам для того, чтобы писать оптимизаторы, но там, в общем-то, оно на практике не очень хорошо работает и не очень предсказуемо. Прогрев такого оптимизатора и обучение занимает очень много времени, и там есть проблемы. Скажем так, с точки зрения научной ценности, да, ценность есть. С точки зрения практической ценности, то если мы хотим там что-то закомпилировать, нам нужен для этого кластер машин, ну, блин, я не знаю. Как бы, если решать задачи дискретной оптимизации, то их можно спокойно решить на одной тачке, радоваться жизни, там, исправить как-то, сделать какой-то кодинг. А если там обучать нейронки, и там, рекуррентные нейронки, и обучать индийскими алгоритмами, там возникает проблема. Тут сложно прогнозировать. То есть там ограниченное количество проходов и в конце неизвестный выход. То есть может заоптимизировать, может нет, может научиться, может нет, неизвестно.
Я вот просто, когда я сказал про нейронки, вспомнил пейпер Anglican, это либо Declosure DSL, которая позволяет писать модели и делать по ним инференс материала. И они, вот у них был такой прикольный демо-проект, где они генерили код, который, собственно, удовлетворяет каким-то арифметическим констрейтам. Там они прям сэмплили из распределения валидных токенов, и у него там получалось волшебным образом валидное выражение.
Ну, там нет никакого волшебства на самом деле. Есть нюансы. С аппаратной точки зрения вообще при кодогенерации в первую очередь надо учитывать очень много факторов, начиная от многоуровневых кэшей, ну, что у нас есть стоимость кэширования, есть кэш-стриминг подходы. Одно дело завязать симды, другое дело заполнить кэш так, чтобы у нас всегда в кэше были актуальные данные. Если у нас есть, грубо говоря, реактивный поток, нам надо, чтобы в кэше всегда были для нашего симда актуальные данные, чтобы у нас нигде способность регистра-консюмера не падала, чтобы его достаточно. Это довольно сложная задача. Ну, она решена там, например, в Open Power отдельно в IBM-овских процессах спеке есть команда для кэш-стриминга на SIM. А в рамках 86 процессоров, то там половину инструкций не документировано, есть пару карточек инструкций. К сожалению, этот вопрос пока покрыт туманом не дает.
Кэш-стринг, как называется?
Ну, проектать инструкции в рамках SSE3, они, половина из них просто даже не документированы. То есть там, в принципе, очень много проблем в плане, что у нас вроде бы Steam есть, но актуальных данных в кэше для обработки нет.
Да, это прикольно, как на этапах специальных программирования обсуждать производительность.
Ну, в маленьких масштабах это, конечно, бесполезно, а когда мы говорим там про какие-то DPI, там, не знаю, какие-то задачи доставки контента, потоковой обработки, там, machine learning, там, классификации в реальном времени, когда мы говорим о верифицируемых языках, там, когда у нас наш функциональный язык можем транслировать спокойно в какой-то красивенький ассемблер, и когда наш функциональный язык верифицируемый можно транслировать, допустим, HDL-веревок, пришивать риски, нарезать асики, радоваться жизни. То есть там в таком контексте оно совсем по-другому выглядит. Там почти все процессы реалтаймовые, жесткий реалтайм, и синхронизация в основном, ну, временная. Там задача довольно сложная.
Чем вы конкретно занимаетесь этой историей?
Сейчас занимаюсь разработкой компиляторов и проектированием функционального языка. Уже давно занимаюсь.
А что за приложение?
Не могу сказать.
Окей.
Да.
Прикольно.
Ну, с IBM работал давно и долго, как бы, контрактором. Крутился в этих open power, это все. Понимаю, там, какие есть накладные расходы, там, как масштабируется простой процессор в enterprise, там, какие метрики есть, какие сложности есть. Там. Часто у людей очень много предрассудков касательно утилизации аппаратных мощностей. То есть, на самом деле, когда мы там смотрим какие-то графики, там, грубо говоря, утилизации, то это всего лишь пару процентов от того, что происходит, ну, в реальности. Мы же не меряем на японских свечах там, утилизацию наших процессоров, там, ну, минимум, максимум, локально не выделяем, это какое-то дискретное промежуток времени. А там на самом деле разброс может быть очень большой. И там очень интересно это все.
Это клево. То есть можно думать, что где-то есть быстрая реализация функциональных языков.
Я потому что быстрая реализация есть, но в основном это верифицируемые языки, это попытка воскресить аду и попытка, короче, верифицируемые языки в рамках функционального программирования транслировать аппаратные решения.
А каким образом там эти программы верифицируются? Там какой-то separation logic или там эти программы в код конвертируются, потом...
Ну, прямо верифицируемый HDL конвертируется. Если функциональный язык верифицируется, значит он может верифицироваться ну, и в рамках HDL. Там правила довольно сложные. Ну, я занимаюсь, у меня есть такая мечта, этим всем занимаюсь просто для того, чтобы разработать язык, который можно было бы там на лайфкоде что-то, там, я не знаю, на своей локальной тачке, там, пошить какую-то плиску и получить там возможность обрабатывать 150 гигабит трафика там, вкладкой за $4000, радоваться жизни. Сейчас как бы, да. Да, ну, то есть, чтобы таких пару платок могли обслуживать какой-то один большой проект, и с точки зрения амортизации, это, ну, просто как.
Клево.
Да.
Это, да, моя личная история, что я последний месяц, наверное, Haskell не пользуюсь. И я пересел, ну, у меня был проект, который, не проект, а программа, которую я писал, в них было 1,5 миллиона строк кода, потому что из них 1 499 было сгенерировано протобуф в стеке тайп-классов. И каждый раз, когда я нажимал Ctrl-X, Ctrl-C, Ctrl-L, чтобы загрузить, короче, буферство, я ждал где-то минут 4, пока этот, собственно, модуль у меня загрузится в GFCI. Пока там скомпилится.
Я тоже смотрел реализацию различных иконографических языков. Сейчас вот
Какие языки?
Ну, иконографические, икономорфные. Короче, сейчас есть нюанс, то, что стоит рассматривать реализацию языков, когда у них уже парсеры, ну, LL, LAL и прочее, они встроены в сам синтаксис языка, чтобы можно было спокойно описывать синтаксисы разные и разные структуры встроенными средствами, там, спарсивать, вводить какие-то ограничения для верификации, и это могло бы упростить задачи кодогенерации, потому что у нас свертка кода происходила бы на этапе лексического анализа вместо кодогенерации. Мы бы поставили там какие-то токены при компиляции, и у нас бы была вместо кодогенерации какая-то свертка лайткодинга. Вместо этих 3 миллионов строк мы бы получали просто какой-то маленький пару функций сгенерированных компиляторов на этапе лексического анализа.
В смысле, какие-то простые оптимизации или просто код?
Нет, ну, допустим, если мы где-то используем рефлексию для кодогенерации, то делать свертки на этапе, ну, на рефлексии, на этапе как раз-таки лексического анализа. То есть, если есть какие-то вещи, которые мы можем посчитать в compile тайме, то их считать в compile тайме вместо кодогенерации. Когда у нас достаточно типов, ну, вот у нас есть SSA, допустим, какое-то. Если у нас, ну, single static assignment, если у нас есть все данные для SSA, мы можем это SSA спокойно транслировать в compile time, то можно спокойно отказаться от задачи кодогенерации. Там все данные в рамках SSA доступны, мы можем спокойно выполнить вычисления на этапе компиляции. И таким образом мы, опять же, если у нас есть возможность обратиться к рефлексии на этапе компиляции, то почему бы и нет? Таким макаром мы можем очень много простить, во-первых, работы, меньше кода, меньше толку.
Хочется программу побыстрее запустить.
Что?
Хочется программу побыстрее запустить. Вот в Виске ты нажимаешь Ctrl Mod X, ну, моментально запускается, потом Shift какой-нибудь.
Все зависит от размера программы, но на самом деле, если мы решаем присвоить кодингу, то, опять же, ничего не мешает это все распараллелить и получать выхлоп реально, ну, в реал-тайм. То есть вот эта вот задача, ну, свертки static single assignment формы, она как раз таки имеет отношение к кодингу, что мы можем получать результаты выполнения этих сверток в реальном мире.
Что в этом контексте ты называешь лайткодингом?
Ну, у нас есть какой-то REPL, мы сразу выполняем наш функциональный язык, смотрим, какие там есть свертки, готовые.
Свертки, это что здесь?
Ну, single static assignment, когда у нас нет неизвестных в этой форме, мы можем сразу производить вычисления. Если у нас есть какие-то переменные неизвестные, мы их отлаживаем непосредственно на этап кодогенерации. То есть смысл в том, что производить свертки в этой форме в лексическом анализе.
Чем раньше ты делал редукцию,
SSA помогает мне делать статический анализ и constant folding.
Ну, это constant folding. Да,
Зачем SSA для этого?
Для кодогенерации.
Для сверток мне SSA не нужен?
Он используется для сверток просто потому, что нам надо его эффективно распределить. Если у нас есть SSA, мы можем положить его на какой-то синт, еще куда-то разом зажить. То есть SSA, там тоже есть несколько форматов новых SSA, я тоже недавно проводил исследование, буквально на прошлой неделе по поводу новых форм, именно SSA для синтов. Наличие SSA и свертки на SSA позволяют как раз таки распараллелить тоже на вот этих вот моделях на графиках. И это реально очень хорошо позволяет ускорить разработку в целом и производительность подобных компиляторов. Ну, сейчас исследования в основном проводит IBM, Intel в этой области. Но, опять же, это многофункциональщина и тоже очень интересная синтаксис языков. Очень много дизайнов рассматривается, отклоняется. И как-то люди думают о том, что будет после C++, потому что C++ уже не похож ни на что.
Кто использует C++? Привет. Классно, по-моему, прикольно. Давайте пока познакомимся, не знаю, пока мы ждем еще Джастина. Во-первых, для тех, кто дошел вот с части зала, потому что вы пришли позже, я говорил, что в этот раз я кинул клич в группу Artificial Intelligence, и получилось так, что у нас сегодня смешанная тусовка, потому что если вы из группы Artificial Intelligence, то не видите в руках руки, чтобы я вас видел. Прикольно. Супер. Скажите, кто не пользуется функциональными языками и интересуется вообще, как бы, идеей возможности применить или нет? Все пользуются, один человек. Прикольно. Привет, всем привет, заходите, садитесь. Вы попали на припати Kievfprog, потому что мы все еще ждем Джастина, и бред несу я сейчас. Собственно, мне интересно, например, кого какие применения функциональных языков в работе. Например, кто пишет только игры, играет дома на этих языках. Есть такие люди, вы хотите пользоваться этими языками в работе, но у вас не получается. Раньше было таких людей много. Вот я вижу одного человека. Прикольно, 2 человека. Остальные стесняются или нет? Вы стесняетесь? Ну что, скажите, или... Поехали дальше. Кто, собственно, пользуется функциональными языками там очень долго на работе уже? Лисперы, например.
Ну, скала находится функционально?
Ну, конечно. Ну, она, конечно, является функциональной, но это не зависит от моего личного предпочтения этого языка. Ну да. Я думаю, что она прекрасно справится. Собственно, я сегодня читал какой-то длинный тред в Твиттере про Swift, а есть Swift программисты? О, собственно, один. Ну, в общем...
Нету какой-то, скажем так, дифференциации, что надо знать много языков.
Ну, да, это такая проблемная деформация людей, которые занимаются языками программирования. Но просто слово твита получилось так, что я, когда был школьником, я читал чуваков, которые занимаются LLVM, и тут внезапно все чуваки, которые занимаются LLVM, стали менеджерами команд Swift.
Да.
Ну, они работают в одной и той же команде, да, в компании все это время. И ребята там сравнивали Swift, как это что будет, если... Ну, собственно, проблема какая? В Swift постоянно тайп-чекинг взрывается в специальные кейсы, потому что там, ну, типа, литералы нужно, там, можно разные типы происходить с этим литералом. И кто-то сравнивал это с тем, что это то, что получается, если ты берешь, надеваешь smalltalk на C, а потом это скрещиваешь с ML. Получается как бы Swift. Я, собственно, это хотел к Scala сравнить, потому что Scala тоже такая ерунда.
Сказали сейчас проблемы с макросами, то что внедрили макросы для кодогенерации, там, и порог вхождения очень большой.
Okay, Justin, hey.
Hey.
All right, good to see you. So hey, this is Justin. Please give him a hand because we're waiting. All right, so we're gonna give you some time to prep. We've been just working out. So the best case is that you're using this computer that's in there. You can just open your, yeah, this is the keyboard of that computer, and this is the screen. So you can just set up by using Twitter, just using links or whatever, or you can just send an email to tap this and great. Yeah, go ahead.
Can't use this tab, is that okay?
You can close everything. Oh, we're streaming live on YouTube.
Oh, hello.
So this is the camera. So I've been working recently with the guys who are doing live streaming. They do it for esports, and they actually have like a TV channel that's like live 20 hours on Twitch, 20 hours per week. And their idea is that like you can stream everything. Like literally, we have people who are playing Sims 4 and they're just talking about how to live your life. We have people who are like they're playing guitars and doing music and playing cardboard games and stuff like that. And from that, I learned that you can like you don't have to be shy to live stream your video. So I've just been streaming this crap for like 30 minutes now, and we have like 2 viewers, and this is like the idea of going live, stuff like that.
Well, text a little smaller, yeah. Some may run off.
Okay, so this is the time to formally start Kievfprog. I've been following Justin's work for quite some time now, and I randomly saw his message on Twitter on Sunday, was it? That hi, I'm in Kiev, there's something going on. So this is what's going on. This is Kievfprog, and we're super psyched to have you here. Yeah, please welcome Justin again, and let's hear it.
Thank you, everyone. Sorry for being late. Traffic's really rough today. So this is a talk. Is the English okay?
Yes.
Okay. So it's going to talk on dependent types, how we can use them to do practical things, not just scholarly, academic, theoretical things. How many of you have heard of dependent types? Okay. This is I guess it's a functional programming group, so a lot of you probably wouldn't. How many of you here use Haskell? Okay. Well, what other languages are used in the context of functional programming here? Scala?
Mostly Scala.
Scala.
Clojure.
Is that Scala Clojure? Okay. Yeah, Scala is closely related to Haskell in that type system is similar. I think Clojure is dynamically typed in a way.
Yes.
So you can use some of this, but mostly we're going to see how the dependent types can be used to do practical things. I know when I started out on this journey, most people using dependent types were using it for very academic things, like how to verify that your list has only even numbers or only odd numbers, which is nice in theory, but really, how often do you need that in your life? So I wanted to make my programs more type safe. Now I was writing neural networks for my research, my PhD thesis. So I thought, well, I'll add types to this and see if it can help me. And surprisingly, it helped me a lot. It made development much faster, more maintainable, more safe, and it became much more a joy to work with these neural networks. And usually you don't hear joy on neural networks, but I had a lot more fun with these neural networks, with these types. So I'm going to go on my journey and how it can be applied in general too for your own applications now. The slides are online, and the code's online too, so you can follow the code if you want to compile along. You're going to need GHC8 and these libraries we're using. H matrix and lone random just are utility libraries, and singletons is just how we tie together all dependent types. Singletons is how we emulate dependent types in Haskell because we don't have them yet for real. Singletons library is how we do. So the big question is, what can types do for us? This is kind of the guiding principle of all Haskell journey, I feel like. When you learn Haskell, a new domain, how can types help us in ways they haven't done before? All Haskell killer apps, all Haskell revolutions, all things that Haskell are good for, start with the question, how can the types help us? How can types guide us? How can types help do things that we haven't done before? So in a way, dependent types is just this mandate, but further. How can we push the types even more than we've been doing so far in Haskell? How can we take all the usefulness of types and even get even more from them, make types work for us even more? So dependent types really, I think, are not special. They're just kind of the same Haskell motivation, just pushed a little further than it had before. So it's just a continuum, not a revolution, but a continuum. So how many of you heard of artificial neural networks? They've been getting a lot of buzz. The main idea is that, well, this talk isn't a machine learning talk. It's just a functional programming talk. So I'm not going to go too much into how it works. The idea is that you get an input vector, and it goes through a bunch of linear transformations with matrices and basically multiplications, and how you have an output. So between each of this array of arrows is a matrix, represented by matrix, essentially, and you basically transform them here and transform them there. So you take one vector, make another vector, and a third vector, and the third vector is your output of your neural network. The goal is that you want to pick the right transformations to get to the answer you want to get. Right? That's the idea of neural network. And the reason why these are popular is that picking the right transformations, these are made in a composable way. Picking transformation, it becomes something that you can do using data and training and a lot of algorithms. So the magic is that because of how these are constructed, we can find the right parameters easily. That's kind of a high-level view of what neural networks are supposed to be useful for. So the idea is basically they're functions from Rn to Rm, and each layer gives a new transformation, and at the end of it all, we get an output layer. And transformations are parameterized by weights, and we want to pick the right weights. That's what you would learn if you were, Neural 101. This is not the important part of the talk's kind of background. So let's try to write the Haskell. So the idea, so we know we have inputs, we take into multiple transformations. So each transformation is a matrix. So we can use Is there a pointer here? Okay. Is this visible at all?
Yes.
Okay. So each layer, we're basically saying that each layer will store as weights, which is a matrix. So we have weights here, and so each layer parameterized by these weights, matrix and a vector. And then we have our network, which is basically a linked list of weights. This type, this syntax is GADT syntax, where we supply our constructors and what they contain. So the network type has two constructors. It has O, which is the output weights, and it has cons, which is the internal weights, and the rest of the network and the final network. So it's basically a linked list. If you've ever seen a linked list, it's basically a linked list, but only for one type, and for weights. It's basically a linked list of weights. Either you have the end of it, the final weights, or you have internal weights, the rest of the network. That's your network. So this is a normal data type. It's not even the dependent type, it's a normal type. We're doing this all untyped so far. So this is how a network might look. We have with the hidden layer, two hidden layers. The output layer was like this. In layer 1, cons with layer 2, cons with the output layer. That's how you would make this in this data. So we have, so it associates this way. So it's that cons with this, which is that cons with that. So a linked list, basically. You will see this in normal Haskell as a linked list. It's like a constructor. Imagine this is just cons. Imagine this is nil, a linked list. We can run them. So we run. This is the actual map of neural networks, which is important. But basically, that's how we run them. We'll run a layer, weights. We give it the weights. We give it the input vector, get an output vector. To run a net, we just do the same thing recursively. We give a network, give it input vector, we get an output vector out return. So give a network vectors. We'll do this. We just do the basic. It's basically a fold, right? This is basically a left fold. A right fold. This is a left fold, yes. So we have, if it's output layer, we run the layer on the input. If it's input in layer, we run the layer on the input and pass on the rest of the thing. So basically a left fold. If you're confused right now, just think of it as this is a left fold on a list with running this function in each one.
Is have greater a dot product?
Sorry, where is that?
Have greater.
Oh yeah, this is the matrix vector product.
Right.
Yeah, so this is the matrix. This is the vector, so it's a matrix vector product plus the bias vector.
So it takes two vectors and just multiplies them around.
Yeah, so it takes a vector and multiplies it by the weight vector plus the bias vector.
Okay. It does the plus first.
Yeah, so every weight has biases and matrix. So the output is the bias vector plus it does this first and adds it to the bias vector. So it's that the matrix times the vector plus the bias.
Okay.
So the actual logic isn't really important. It's just the fact that we do some math in it. The math isn't the important part. Just know that the important part is the types. Weights and vectors equals vector. Network plus vector equals vector. So the math is super important. It's just the fact that we have math and then types. So making new ones is kind of something you might do using a list. This is a traversal. So this is how we might have the make of new weight. We might have the user give two dimensions, the input and output dimensions, and then return the weights using just monadic, a source of entropy somehow. The important thing here is the type signature. Give it the input size, output size, and we get random weights in return. We make a random initialization of weights. And then we give the input size of our internal layers, and output size, and we get a random network. So that's how a user would run these functions. Give an input, output, and get weights in return. Input size, output size. And here we have the input size, in layer size, output size, and a network in return. So that's how a user would use. And then you might ask questions. Which one is which? Like, what if I was a user, I was writing random weights? How do I know which input was the first one output, second one input? It's not really obvious. So you have to be really good at documenting your function this way. Same here in networks. Just think at this, which one is the inputs? how many we need, what's the download sizes, how many outputs we have. It's not really obvious from the type, and we need to have the user view documentation. And also a lot of these, also important thing is how are we as a writer know that we write it correctly? See, we're using here, we put O here and I there, but what if we had put an O either and O by accident? What if we were tired, sleepy? What if we switched these two by accident? They're both ints, right? So there's no way that the compiler will help us. What if I, instead of having the first layer be IO, what if I did OI as a writer? This bug in my program, I might never see until it's too late. So as a writer, this is scary because what if I did both ints, I can switch them easily. It's not really, you have always, this is the next section, Haskell heart attacks. So you problem Haskell, these things I mentioned are instinctually ground into you from day one. What if we mix up dimensions? What if we switch the two by accident here? What if we had done this by accident there? They're both ints, so the compiler would just be okay with that. What if the user makes up dimensions? Okay, so a user would need to look up documentation, and what if the user read it wrong? What if the documentation is not available? What if they're on the plane, they can't read documentation? There's no way to really know which input was where except for documentation. And documentation is not a really good substitute for safety. And what if layers are completely incompatible? What if I actually what if I had stuck in bad layers here? Or what if when I was making my layer here, I switched these two? That would be compatible. H2 might take 10 inputs. H1 might give out 5 inputs. It might be incompatible. But we can put them together just fine. Same thing for TensorFlow, right? TensorFlow or any other neural network library, you can con together two incompatible. Actually, I think this one might have some verification after the static part. But in a lot of libraries, you can con together two incompatible layers, and the compiler will be okay with letting you do it. It's just not something that will stop you. You can do the worst things in the world, but it won't stop you. And also, if I have a network, if a user, I get no network type of user, I get this type of user, network. Neat. What do I give to my network? So here, run network. I get network. What is it expecting? It's expecting a 10 input vector, expecting a 5 input vector, expecting 0 input vector. There's no way to know from the type. We have to kind of query the network, get things done at runtime. There's no way to know what the network expects, and no way to know what it outputs. These are all things the user can't know is opaque to the user. Not a lot of danger happening here. So there's no way a user will know what type of vector the network expects, or what size it expects. And also, are these correct? Now, I told you earlier to trust me if they're correct, but should you trust me? Right? You shouldn't trust me. If I was a coworker and showed you this, I showed you a bunch of math like this, do you trust me? You probably shouldn't trust me. You should look into deeper, or hopefully the compiler will tell me it's correct or not. The compiler will tell me you did it wrong, you did it correctly. But without compiler, just me, you trusting myself. You can't. And I think I wouldn't trust myself either. I wouldn't trust myself for things like this. Math isn't intuitively easy to get right the first time for things like this. Basically algebra. I mean, basically arithmetic. So as me writing it, you can't trust me that real quickly. I can't trust myself. If I'm writing it at 2 a.m., I commit it, I compile it, I wake up next morning, I have to make sure I did it right. No, I trust myself from last night that I did it correctly. These are all things that Haskellers kind of learn how to internalize as they write code. But at this point in Haskell, we can't really address these concerns, but maybe we can. So let's add, oh wait, this is the last kind of worst example of bad things. So reading this, you should feel worried reading this. How to train networks. So you train network by giving a learning rate, and input vector, and target vector, and then it'll update network's weights. So basically train that you give it an input and what you expect it to get, network will update itself to make it to match the input output relationship. So again, already you see what are some problems already here, some of the obvious problems. What if I give the wrong input size? What if I give the wrong target size? There's no way to know. Then this will all fail runtime. The compiler can help you. The compiler won't help you write it. It's going to fail runtime. And when you're writing it, you don't know what to expect. So this is kind of a mess. Don't worry about it. I think I pressed wrong. They're waiting for a second.
I'm going to find.
Sorry, I pressed the.
Hi, everybody.
I think the TV is off as well, so I'm guessing it's something with
on the computer maybe. Sorry.
Should they receive good?
Oh wait,
Just a second.
I think I have some iTunes icon over there. Maybe the user is running. Try like using the that button.
The tab.
There's a trackpad on the right thing. Yeah.
Okay.
Maybe the content.
Okay. I'll just refresh it maybe. Is that how you refresh it?
The URL said dependent times, maybe it's important.
Yeah, whoever intended Safari should use different types. Or at least the color should.
Something goes wrong. Can somebody share
The actual slide.
I have open slides. Maybe it helps in PDF.
I think I can use a new browser window, probably fine. Use a new window.
What if you like go outside the full screen and try to see like the window boundaries? Very like.
I can use this here.
Where's the secret key? This screen black is this.
I guess the key has a B on it. Maybe B stands for black. Yes, that was the black. I can't see this. And the code, okay, so. With application, this should be looks kind of scary, but because it is, writing this math is a lot of math, and the key point here is that at any point in this place, there could be a mistake, a bug, and most of these bugs, almost all these bugs, will not be caught by the type system. A lot of arithmetic, vector, the trace here, and the outer product. Most of these will be typed by types, and it's really kind of not fun to write. I remember when I wrote this first time, I wrote it, I had to do it. I wrote it wrong many times before I wrote it correctly. I got it wrong many times, and I couldn't check it until I went in and actually checked the math. I had to check I trained on sample data points. I wouldn't even be sure if it was correct or not. A lot of times you might end up get some code. But if you're lucky, the error will come right away when you run it first time. If you're unlucky, the error will come until you have to do a lot of things to get it out. But yeah, so a lot of operations, run layer, logistic function, go on, go O and N. But a lot of it is unchecked. So it's not fun to write. It's a lot of guess and checking, making sure if you're really good at vector algebra, vector calculus, then it'd be good for you. But otherwise, it's a lot of guessing and checking that's correct. Anyway, so where's compiler in all this? It doesn't help us. Haskell's all about compilers helping write your code. Compiler doesn't help us at all there. There's no way it can help really. It can help you check your syntax. That's really it. And how can the shape matrix help our programming? How can we use this to help us as a programmer? And how can we, basically at this point, I'm relying on naming conventions to write our code correctly, right? I make sure it's called ON, OM. I'm labeling correctly, make sure I multiply correctly. But conventions are no substitute for correct code, for actual type code. Conventions are naming conventions are no substitute for types. So let's see if we can do better. And a red flag. So how many ways to write function has no type check? This is kind of a Haskell red flag. How many are partial? How many functions have been partial? Pretty much all of them, right? All our functions so far have been partial. By partial, I mean they don't run with all inputs. So you can give them the wrong inputs and they'll fail at runtime. All functions, they're not defined for all inputs. So all functions we've done so far, the train function, the run network function, the raise function, all of them are partial in that they will fail at runtime and they're not complete functions. So these are all kind of things that Haskell as we've learned to accept as red flags when we look deeper. So let's look at an alternative. So the HMatrix library offers a type vector and type matrix type. So this RO here is a vector of O real numbers. So instead of saying vector, we say RO, and O is how many real vectors, how many numbers are in the vector. So R5 would be a 5 item vector. R8 will be an 8 item vector. R100 would be a 100 item vector. Here, LOI is a matrix with O rows and I columns. So an L8, 10 would be a matrix with 8 rows and 10 columns. Here's kind of the types of RNL, or the kinds of RNL. R3 is a 3-vector, and L43 is a 4-by-3 matrix. So the type of the matrix, the size of the matrix and the vectors are in the types. Important. Also, the operations too are also types, right? So adding 2 vectors right here, you can only add vectors of the same length. Already improvement. I can't add an R5 and an R10. You can only add vectors of the same length. And matrix vector multiplication, I think should be found other than what I'm saying before. You can only multiply vectors and matrices that match types. So an n by n times the n is equal to an n, which is kind of what you're expecting from linear algebra matrices. So we can multiply a matrix by the wrong vector, multiply a vector by the wrong vector. Everything is types. And also, even if we use type code, if we had plus underscore in Haskell, it'll tell us what in scope can go in there. So we can help write our code. So if I wrote Haskell, I wrote x plus underscore, that would tell me what in scope can fit there. And usually it's only one thing. So if I typed in my matrix at W multiplied by underscore, it'll know exactly what vectors in scope can go in there. And that way we can pick the right vectors just automatically. So this kind of helps us. The no-net constraints, these are used by H matrix. You kind of basically say they need this constraint to do the math. So don't worry about it, what is right now too much. But it's basically a type constraint on the numbers that lets it do the math. So type hold in Haskell are great. You can have blank multiplied with my vector, and it'll say, oh, what matrices are in scope that have this shape? It'll tell you right away what can fit. It helps you guide your writing. So just to clarify with data kinds, it's the kind of Haskell concept. You can all Haskell values and types are also types and kinds in the latest Haskell. So we have a list type, we also have list kind, and we also have type level lists like this. So the type of true is bool, the kind of the type true is bool, and the type of true false is a list of bools, and the kind of this type. So K is types and T is values. So this type has this kind. So this list is a type. It's a type level list. So it's something you see in your type of type. So we're going to use it here. A network here it takes an input size, a list of pin layer sizes, an output size, and is a type. So again, basic instruction just now with types. So if I had an OO, that'd be a network 5 no input layers. And so okay, so if O was weights 5, 2, meaning input 5, output 2. A network O would be a network with input 5, no in layers, and output 2. Now this H2 here was a weights with 8 in, 5 out. Right? It would be counted here and get network 5, 8, 2. And if I had H1 cons H2 cons output, we get network 10, 8, 5, 2. And then if we switch the 2, we get type error. This won't compile. If we switch the 2 layers, it won't compile, it'll be type error right away. Everyone understand this kind of how I got these numbers here, how it works, how they compose together? So if my output layer has 5 input, 2 output, then the network looks like 5. This is the type of network. The type of network would be 5 million layers and 2 output. So the list inside this list here, the type level list here, is list of the size of all the input vectors, of all the hidden layers. So see how they build up really nicely? It's like a chain. So basically like a chain. So going from H1 to H2 to O, you can go from 10 to 8, 8 to 5, 5 to 2. Nice progression, nice waterfall of numbers of vector sizes. Okay, so write them, same code exactly, it's a trick, same code. Exact same code, same letters, same everything, same symbols, but now it's verified by the compiler. There's no way to write this. Well, there's some way to write this. There's most ways to write this wrong are now gone. Same thing here. Writing this wrong way is now really hard. We have to really try to write this correctly. The way I write it correctly, the way to do this wrong is of course any constant vector counts. So if you put like constant vector zeros here, it would break. It would be wrong, of course. But you have to be trying really hard to make this not do the correct implementation. When I wrote this here, if I leave underscore here, I would say, oh, did you mean WN? That fits there, and you can use that exactly. So kind of like an IDE-driven development, right? You can leave an underscore here, and I would say, the only thing that fits there is this thing you gave me here. So it basically writes itself. Here also, we need a V. So if you run it on the inner layer, you need V the right size. Only way to get that is to run the rest of the network. So only way to get a V of the right type is to run the network on the rest of the network. So this kind of writes itself as well. But the powerful thing is that it's the same exact code, just now it's checked with the compiler. So basically you get all this verification, this correctness for free. It comes for free. You don't need to rewrite anything. It's all the same precedence, same readability is the same, but now readable plus is correct, which is better, right? Readable alone is nice, readable correct is even better. So running it is also nicer. Look at this type, isn't it beautiful? Network I HSO, so you know it needs an I input and an O output. There's no way to mess this up. If you're a user, you run a library, the compiler will tell the user exactly what it needs and what goes in, and then if it's wrong, it will even compile. It will fail before it compiles. We moved runtime errors to compile time, which is the kind of overarching goal of a lot of what Haskell is known for, what we do in Haskell, what we're all about. So the user using this, if you see this type in your documentation in your module exports, you know exactly what it does. You know, it takes the input layer, the measures I, turns O, measures O. So build network 10 something 5, you would give it R10, which turn it R5. And you know this without running it. You know the user, the user, no way to mess it up. And generating awaits also is even better too. See, before the user had to know which input was input, which input was input output. But with this, the type of the input output is in the actual type. Type is in type. The size is in type. So all these things are automatic for you. I as a writer can't mess this up. I can't give them the wrong matrices. And as a user, I can use this easily. I know what I expect just by asking for a type inference, right? If I want to weights 5, 2, I don't have to go run weights int 5, int 2. Just automatically do that state from the type inference. So like in Haskell, there's a very function, the read function, right? You read a string into a type of your choice. You don't need to say read this string as a bool, or read the string as a list, or read the string as a int. The type system knows what you want it to be based on type inference. Same thing here. We can have the user exactly know the user whether that's what they want exactly without any input, just from type inference. Generating network is actually a little harder because we have a problem. How much time do we have?
Yeah, 20 minutes.
Okay, so this is kind of this is the complicated part of pantypes. So it's a little interesting because what if we want to make a new network based on what the user wants, right? The user wants maybe 5, maybe 10, 5, 2, and then 1 output. So how do we make this? The problem is that we can't pattern match on the types, right? That's kind of the issue. We want to say if it is empty, give us just an output layer. If it's 2 items, give us input layer and output layer. This is hard in Haskell because types are erased at runtime, at compile time, at runtime. The problem here is that this H in a type doesn't exist in Haskell at runtime. So the types is here. When you compile the code and you run it, this H is gone. So there's no way to actually pattern match on those H's. So this is actually a problem. This is why Haskell alone isn't quite there yet. That's why we need dependent types to actually make this possible. In the future, it'll be easier, but for now, we have to kind of use singletons to substitute for dependent types. So singletons library lets us pattern match on this type here. Let's go review singletons. Singletons are types where you can pattern match on them and get the type in that it was used to be. I'm sorry, that's really badly stated. Let me show you an example. So the singleton s false has a type sing false. This is pretty mechanical. The singletons s true, cons s false, cons s nil has a type sing true false, true cons false, cons nil. The singletons nat one, cons nat two, and cons nil has a type 1, 2. So this is the actual types here, but the important thing is that if I see a s false, I know that the type is false. If I see a s true, cons, if I see s con, I know the type is true, cons false. So by seeing the value, we see the type. That's kind of the key here, how we use singletons. And so, as a final thing, we can now make our random networks. So we have to give, so the user has to give a singleton with the type H's to get the network. And then there is straightforward, just like before. If the type, so if we see s nil here for singing H's, we know that it's no hidden layers. So we return the output. If we see the cons, means that cons, there's 2 hidden layers, at least 1 hidden layer. So use cons. So the main point here is that we have to pattern match H's somehow to get the H's in the list. So we use H's to know, we use the singleton to know what's in H's to get us, and then we can do our work. The advantage here is that instead of, remember before we passed a list of hints, now we passed a list of singletons. Why is that better? What did we gain? Right, because before we passed a list of hints. Now we pass a list of singletons. Same thing, right? So actually, we gain a lot. One thing we gain is that the list we have here corresponds with the list of our network. We know that already for sure, right? So if I passed in before we had ints, those ints might be unrelated to the network type, the network size. I might use ints. I might use lists incorrectly. I might use the ints incorrectly. I might use them backwards. I might skip some of them. I might just use it wrong. But if I pass a singletons, I know that I return something that's correct. So the singletons make sure that my annotation is correct and verified. If I just pass a list of ints, then I could be wrong, but here make sure this shows that I'm right with what I write. This compiler makes sure that whatever singletons I pass in for this, up to the network's shape here. That's what we gave me from singletons. What we lose kind of the niceness of it. Because before, we didn't need to pass in an extra value, it's kind of ugly. And now we pass in the values, it's also ugly. We kind of want to get rid of that. Luckily, we can have a type class, we can get the staying on demand. So now it's the same thing up here. So this is the same, now it's the same thing here, but instead of passing in the singleton explicitly, we just have the type class go to us on demand. So now we have a nice, this is the actual final interface you might see for a user. So this is kind of the original API we wanted. Just generate a new network I to O, you type in friends, no inputs required, boom, it works. Right? The user doesn't have to worry about anything. Right? Input, outputs, in layers, it's all inferred by type system, it all works out. It just works. It just works. So just whatever name you want is generated by the types when you type in friends. So that's kind of the at least part of this library, of this talk. And right now we have to use, because Haskell isn't really there yet, but we use singletons right now as a crutch. But the end API is really nice. Just generate a new network with the input layer, in layers, output layer, all inferred from type inference. Type inference, so we can't mess things up. And as a user, I know how to call this. As a writer, I can write this incorrectly. There's no way to write this incorrectly. This is kind of verified types. I can write it badly. And also, if we wanted to, we can provide them using this syntax in Haskell. So if we want to go back to our system where we had listed ints, we can do this in Haskell. This is not going to use it. If we really like to write it using explicit inputs, we can always use this in Haskell. if you wanted to. But I like this. I like this a lot better. Just all typographics. So backprop. So nothing changed. You're ready for this? Are you ready for this? What does it look like? Is it much complicated? Is it more cleaner? What does it look like? It's the exact same. Good question. It's identical. All the logic we use is the same. All writing is the same process, except now it's verified correct in a sense, in a lot of ways. There's a lot of ways of writing this incorrectly is now gone. And also when we write it, we have a lot of help with the compiler. Right? So if I had left underscore here, the compiler go, hey, you need something here this size. How about these things? And the things they can put here are very restricted by the size, by the type, by the size. So you know exactly what goes in there. A lot of times compiler will give you exactly what you need. Like here, and you need this underscore like go on what? Like who knows what goes here? Underscore. Compiler will tell you, oh, do you mean this value here is the only thing that fits that type? At this point here, the only thing that fits this type is this value here. Nothing else in this whole function will fit there except for n. Compiler can know that for you. They'll basically write the code for you. It's written for you. No. So this is the same complicated code, but it hides the fact that writing is a lot more simple. And it's a lot more correct too. And I think it's nice that we gain all of the type safety, the correctness, the verification, the type inference, and we don't lose any specificity. We don't make codes the same exact complexity, just the complexity before. It's not any more complicated, it's the same exact code. We gain all this stuff without any sacrificing specificity. Which is kind of, people always say that that's the downside, is that when you have more powerful types, you lose the writing is harder, it's less expressive. But here shows this is exactly that's wrong. At the same time, you guys have more powerful types and have the expressive writing really easily. You have both your cake and eat it. So the whole overarching goal here, the overarching philosophy here is called type-driven development. This term I think invented by I forgot his name. He's the writer of it. Yes, Edwin Brady. Yes, that's why I hear from him a lot. I think he invented it, and his book is actually called Type-driven Development. So the main process, is one, write your program untyped, what we did here. Two, realize all the red flags. Any functional functions, any ways anywhere where function may be implemented more than one way, that's maybe incorrect. And anywhere where the API is unclear or documentation reliant. Where are these happening in our code? We add types in gradually to handle these situations, bit by bit. So I have right now input outputs. That's one way to add types, but you can even add more types to this to make it even more correct. If you are familiar with networks, you might notice that there's other places where I can write it correctly there. You can if those are things that you care about, you can add more types to make even that safe. So you can selectively add in more correcting verification, more these problems being fixed by adding in slightly new, more types every time. It's not good, but I don't think going the other way. Don't go backwards. Don't make your types perfectly correct and then write your thing, because that's kind of really a way to get yourself a lot of headaches, right? Too much types is bad, of course, but if you start untyped, write how you normally write, just gradually add in things where you see these problems. That's where you add types in, and you get a nice gradual thing where you can add this gradual and really clean way. And yeah, other links here. I have a blog series that can this even further. There's new piece coming out soon, and other YouTube links and other kind of type tutorials are here on this thing. And that's it. Yes. Thank you. Any?
I have like 2 questions. Like if you go to the previous slide, so this is like the exact opposite way that Colin McBride does it, right? He writes super complex types, and he just uses sequence 8 as the implementation.
Yeah.
And it just works out.
Yeah.
Well, Edwin's interpretation is also the opposite, because he writes types and then uses types to infer terms.
Maybe is where I differ from him. Yeah.
But well, this approach is also verified.
Yeah, in Haskell maybe it's different because Haskell adding types can be hard. In Idris, it's really easy.
Yeah.
So that's why in Haskell you don't want to go overboard. And if you're working on a project with people who are other humans, they probably would appreciate a bunch of types and then So I think it's best in Haskell today, at least in a few years, to start untyped and go slightly more and more. I should probably be reading this slide then. Reading this slide too. Another type of development. And type. The Haskell substitute for type development.
Let's go to the train function. So you could use gradients manually.
Yeah.
So the AD library, super complex. Do you think it's actually possible to use any of the dependent type tricks if you want to use reverse mode AD from Edward's website?
Sure, yes, it's because I actually wrote a library that does that. Is that why you asked this? Because I wrote a library that I put up a couple months ago.
Oh,
exactly that, yeah.
Okay.
I use dependent types for backprop, something like this, yeah. Oh, so yeah, the answer is yes, it's possible.
Okay. But you cannot use the AD library, right?
Not the AD library. You can't because all operations in the AD library are monomorphic.
Right.
So here, the multiplication, back multiplication is a polymorphic function, as in you pass them to the different types. So you pass them the vector and it matrix the other. The AD library can only handle things that are same type but same type. So that's why AD library can handle it. So my library that I'm developing called backprop, it can handle polymorphic, multi-typed expressions. So it's possible. This is all very new in Haskell, right? Only a couple of years. We're still figuring out the best way to do this in Haskell that isn't ugly, that is usable in Haskell. That's kind of the bridge, right? The bridge between dependent types, Idris style, which is very nice, Haskell, where we have to do a lot of things, hoops to jump through. The best way to bridge it is kind of where we're at right now, trying to find that best way.
You say you take the cafe's model file, right? So
Yeah.
you actually generate Haskell code from it, and then let the user use it. And,
Like a kind of model file? I mean, you could, but
yeah.
I mean, you can maybe generate a network from the cafe model code, probably. I mean, we don't like generating Haskell code. Yeah.
So basically, we replicate what the cafe model says, right? It says here's a layer, it has this size.
Yeah. With actually a couple libraries actually. So this blog post happened a year ago, and the library has that called a Grenade. It's not mine, but he used this techniques and made a automatic backprop library where you use this layer, that layer, you get a network that works automatically from it. It's called Grenade, and it uses this technique basically internally. Well, it expands on it using different layers, not just V4, but also recurrent layers, convolutional layers, but all type-driven, all type inference-driven, safe and all that. So this can go further to a more generic neural network system as well, I guess.
So correct me if I'm wrong, but doesn't next Haskell release 8.2 will be much closer to having nice dependent types?
So I think the time frame is 8.4, 8.6. 8.2 actually just came out a couple weeks ago, but 8.6, 8.4 is where the time frame is, I think. 8.2 actually offered very little in terms of types, so I was kind of disappointed. But I mean, I can complain. I mean, I'm not writing it, so I can't complain.
Yeah.
I'm sure it's really hard, but I'm sure it's not easy. But yeah, 8.4 Idris, something to make it really simple, a very clean, full dependent types. Probably 8.6, maybe 2 years from now. But for now,
So
yeah.
how do you think will your code change when it's out?
You might not need singletons. You can just match with types directly.
So you will not write all this sing.
You can just pretty much on H's. If H is nil, then it's H.
Okay.
Yeah.
You just say case, the type thing.
Yeah, case H is here we had to do case. We had a case match on the singleton, so we can maybe call the case match on the type.
Actually, can you use type classes to pattern match by type level?
Yeah, type classes are a way, because that's basically what Sing is. But type classes, the problem is that they're all ad hoc, and you have to basically have a type class for every operation you want to do. Like a type class for general networks, type class for program networks. Singletons helps you by unifying. It basically replaces type classes in a unified way. Like if you use type classes, you can use type classes to make this. That's true. You can have a type class that makes networks, and write an instance for every size, every size. You do the same functionality. We have to do that for every single function you write as a different type class. That's kind of how type classes have to work. So this function you use type class is the function, but if you want to do another function on networks, you need another type class, another one, another type class. That's why it's kind of more, singletons are a little nicer in that way. And also being able to match IHs is nicer in that way too. It's a more unified way of doing it. Does that make sense?
Yeah, one last thing for me. So I was listening to this last episode of Haskellcast, podcast with Richard Eisenberg about dependent types. It was very good. So they were discussing this other approach that's available, which is liquid Haskell.
Yeah.
Which is basically, instead of trying to put this all in types, to write rules that the length of this thing must be the same as the length of this thing, and then use theorem prover. So have you?
Yeah, I actually went to school with the Haskell team. They were at UCSD and that's where I went to school. So I work with them a lot. It's nice, really great. I think there's a lot of overlap in liquid Haskell in terms of liquid Haskell is a refinement type system where you refine your types at compile time. You use a set predicate type, and then the preprocessor will make sure that your preprocessor will basically be a static analyzer. Make sure your program respects those invariants before you compile it. They're similar. I think 10 types. The difference is that you can manipulate these. So different types can emulate liquid Haskell in a lot of ways, but the difference is that 10 types lets you manipulate those refinements as first-pass things, right? So in refinement types, your refinements are part of the syntax of the language. They're separate from the language. Yeah. But in dependent types, these predicates, these refinements, are things you manipulate as values. So it's a little different approach. But sometimes you don't really need to manipulate a refinement, is what it is in compile time. But I think that's the difference there. If you want to say, might have a value, maybe it has to be between 0 and 10. That's the thing you do with refinement types. But singletons, you can say between 0 and n, right? 0 and an arbitrary number at runtime. So you want to manipulate your refinements at runtime as first-class things. You need dependent types.
Okay, so in liquid Haskell, you cannot say that whatever I get from the network, you should be less than this number, for example.
Yeah, or it might be, you might be doing it in an extreme way, but in general, they're not first class. They're not manipulate as part of the language. They're a separate meta language. They're not like first class concepts.
Yeah.
Okay.
Right, if there are no more questions, then we have, well, let's thank Dustin again. We have an announcement from our friends in Grammarly.
Yeah. Hi, everybody. Thank you for coming. I think I'll switch to something more local. Just language. Итак, всем привет еще раз. Завтра у нас тут для тех, кто любит не только писать на Haskell, а еще и на F#, будет прекрасный митап от одного из наших инженеров об использовании F#, реактивного программирования и схожих подходов в написании UI, собственно. Да? Приходите, кому интересно, можно в фейсбучике на нашем Grammarly Kyiv, на нашей страничке найти, ивент зарегистрироваться и прийти. Собственно,
насколько?
В 7 вечера. Там вон плакат на стене. Там написано когда, во сколько, и, наверное, ссылка. Нет ссылки, в фейсбуче ссылка. Спасибо. Хорошо.
Okay, so this marks the end of the Kievfprog and the end of summer. So thank you all for coming, and see you in fall. Yeah.
Thanks.
Работать
Прямо из...
Ну, она...